Welcome. Today we're diving into the concept of compiling in computer science. Compiling is a fundamental process that transforms human-readable code into something a computer can execute. Whether you're a beginner or just curious, understanding compiling is essential for anyone interested in programming or technology. In this video, we'll break down what compiling means, why it's important, and how it fits into the broader world of computer science. Let's start by exploring what exactly compiling is and why it matters for software development. Compiling is the process of converting source code, which is written by programmers in languages like C or Java, into machine code that a computer's processor can understand. This transformation is handled by a special program called a compiler. The compiler reads the entire source code, checks it for errors, and then translates it into a new file that contains instructions the computer can execute directly. This process is crucial because computers can't understand high-level languages without this translation step. Source code is the set of instructions written by programmers using a programming language. It's designed to be readable and understandable by humans, making it easier to write, debug, and maintain. However, while humans can read source code, computers cannot execute it directly. That's where compiling comes in. The source code acts as the starting point for the compiling process, and its clarity and structure are vital for successful compilation. After compiling, the output is machine code. This is a set of binary instructions that the computer's processor can execute directly. Machine code is not meant to be read by humans. It's a series of ones and zeros that tell the hardware exactly what to do. The transition from source code to machine code is what enables software to run efficiently on computers, bridging the gap between human logic and machine execution. Compiler is the key player in the compiling process. It takes the source code as input, analyzes it for errors, optimizes it, and then generates machine code as output. Compilers are designed to catch mistakes in the code, such as syntax errors, before the program is run. This helps ensure that only correct and efficient code is executed by the computer, making software development more reliable. Compiling is essential because it makes programs run faster and more securely. By translating code ahead of time, compilers can optimize the instructions for the specific hardware, resulting in better performance. Additionally, compiling helps catch errors early, reducing the chances of bugs making it into the final product. This process is a cornerstone of modern software engineering, ensuring that applications are both efficient and reliable. Not all programming languages are compiled, but many popular ones are. Languages like C, C++, and Java use compilers to convert code into machine-readable instructions. Other languages, such as Python or JavaScript, are typically interpreted rather than compiled. Understanding the difference between compiled and interpreted languages helps programmers choose the right tools for their projects and optimize their workflow. Compilation and interpretation are two different approaches to running programs. Compilers translate the entire source code into machine code before execution, while interpreters read and execute code line by line at runtime. Each method has its advantages. Compiling often results in faster execution, while interpreting allows for more flexibility and easier debugging. Knowing when to use each approach is a valuable skill for any programmer. The compilation process is divided into several stages. These typically include lexical analysis, syntax analysis, semantic analysis, optimization, and code generation. Each stage plays a specific role in transforming source code into efficient machine code. Understanding these stages helps programmers write better code and troubleshoot compilation errors more effectively. Lexical analysis is the first stage of compilation. During this phase, the compiler scans the source code and breaks it down into tokens, basic units like keywords, identifiers, and symbols. This step helps the compiler understand the structure of the code and prepares it for further analysis. Lexical analysis is crucial for detecting simple errors and ensuring the code follows the correct format. Next comes syntax analysis, where the compiler checks the arrangement of tokens to ensure they follow the rules of the programming language. This phase builds a structure called a syntax tree, which represents the grammatical structure of the code. Syntax analysis helps catch errors like missing semicolons or mismatched parentheses, making sure the code is logically organized. Semantic analysis is the stage where the compiler checks the meaning of the code. It ensures that variables are declared before use, types are compatible, and operations make sense. This phase helps prevent logical errors that could cause the program to behave unexpectedly. Semantic analysis is vital for maintaining the integrity and correctness of the software. During optimization, the compiler improves the code to make it run faster or use less memory. This can involve rearranging instructions, removing unnecessary steps, or choosing more efficient algorithms. Optimization is a key benefit of compiling, as it helps software perform better on different hardware platforms. Final stage of compilation is code generation. Here, the compiler produces the actual machine code that will be executed by the computer. This output is typically a binary file or executable that contains all the instructions needed for the program to run. Code generation marks the end of the compiling process and the beginning of program execution. One of the compiler's most important jobs is to detect errors in the source code. These can include syntax errors, type mismatches, or undeclared variables. By catching these issues early, the compiler helps developers fix problems before the program is run, saving time and reducing frustration. Effective error detection is a hallmark of a good compiler. In addition to errors, compilers often provide warnings. These are not critical mistakes, but they highlight potential issues that could lead to bugs or unexpected behavior. Warnings help developers write cleaner, more reliable code by drawing attention to risky practices or ambiguous statements. Some compilers generate intermediate code before producing machine code. This intermediate representation is easier to optimize and can be used to target multiple hardware platforms. By using intermediate code, compilers can make the compiling process more flexible and efficient. Cross-compilation is when a compiler generates machine code for a different platform than the one it's running on. This is useful for developing software for embedded systems or devices with different architectures. Cross-compilers enable developers to build applications for a wide range of hardware from a single development environment. Just-in-time JIT compilation is a hybrid approach that combines compiling and interpreting. With JIT, code is compiled into machine code at runtime, rather than ahead of time. This allows for optimizations based on how the program is actually used, improving performance in dynamic environments like virtual machines. Static compilation happens before a program is run, producing a standalone executable. Dynamic compilation, on the other hand, occurs while the program is running, allowing for real-time optimizations. Each method has its strengths. Static compilation offers predictability, while dynamic compilation adapts to changing conditions. There are many compilers available for different programming languages. Examples include GCC for C and C++, javac for Java, and Clang for modern C++. Each compiler has unique features and optimizations, but they all share the same core goal: transforming source code into efficient machine code. Open-source compilers are freely available and can be modified by anyone. They encourage collaboration and innovation within the programming community. Popular open-source compilers include GCC and LLVM, which support a wide range of languages and platforms. Proprietary compilers are developed and maintained by companies. They often offer advanced features, dedicated support, and integration with other tools. Examples include Microsoft's Visual C++ compiler and Intel's C++ compiler, which are widely used in industry. Integrated development environments (IDEs) often include built-in compilers. IDEs provide a complete workspace for writing, compiling, and debugging code. This integration streamlines the development process and helps programmers be more productive. Many compilers are used from the command line, allowing developers to automate the compiling process with scripts and tools. Command line compiling is powerful and flexible, making it a favorite among experienced programmers who want full control over the build process. Build systems manage the process of compiling large projects with many files and dependencies. Tools like Make, CMake, and Gradle help automate compilation, linking, and packaging, making it easier to manage complex software projects. After compiling, the linker combines different pieces of machine code into a single executable. Linking resolves references between files and ensures that all parts of the program work together. This step is essential for building complete functional applications. During compilation, source code is often turned into object files before final linking. Object files contain machine code for individual parts of the program. They make it easier to manage large projects by allowing separate compilation and linking. Libraries are collections of precompiled code that can be reused in different programs. Compilers and linkers can include these libraries during the build process, saving time and effort for developers. Using libraries is a common practice in modern software development. Libraries can be linked statically or dynamically. Static libraries are included in the final executable, while dynamic libraries are loaded at runtime. Each approach has its pros and cons, affecting program size, flexibility, and performance. Before compiling, some languages use a preprocessor to handle directives like macros or file inclusions. The preprocessor prepares the source code for the compiler, making it easier to manage complex codebases and automate repetitive tasks. Debugging is an important part of software development. Compilers often include options to generate debugging information, making it easier to track down errors in the compiled code. Debuggers work with this information to help developers find and fix issues efficiently. Compilers offer various optimization flags that control how code is optimized during compilation. Developers can choose to prioritize speed, size, or debugging ease depending on their needs. Understanding these options helps create better performing software. Compiling code for different platforms can be challenging. Portable code is designed to work across multiple operating systems and hardware. Compilers and build tools help manage these differences, making it easier to develop cross-platform applications. Compilers play a role in software security by enforcing language rules and detecting unsafe code. Some compilers include features to prevent common vulnerabilities such as buffer overflows. Secure compiling practices help protect applications from attacks. Compiling for embedded systems requires special considerations. These systems often have limited resources and unique hardware. Compilers for embedded development are optimized to produce small, efficient code that runs reliably on constrained devices. Cloud-based compiling services allow developers to compile code remotely using powerful servers. This approach speeds up the build process and makes it easier to collaborate on large projects. Cloud compiling is becoming increasingly popular in modern software development. Continuous integration (CI) systems automatically compile and test code whenever changes are made. This ensures that new code works correctly and integrates smoothly with existing software. Compiling is a key part of CI workflows, helping teams deliver high-quality software quickly. Mobile app development relies on compiling code for different platforms such as Android and iOS. Each platform has its own tools and compilers, requiring developers to manage multiple build processes. Efficient compiling ensures that mobile apps run smoothly on a variety of devices. The way code is compiled can have a big impact on performance. Compilers can optimize code for speed, memory usage, or power efficiency, depending on the needs of the application. Understanding compiler options helps developers create high-performance software. Modern compilers work closely with debugging tools to help developers find and fix problems. Features like breakpoints, stack traces, and variable inspection make it easier to understand how compiled code behaves during execution. The field of compiling continues to evolve with new techniques and technologies emerging all the time. Advances in artificial intelligence, cloud computing, and hardware design are shaping the future of compilers, making them smarter, faster, and more adaptable. Learning how compiling works is a valuable skill for any programmer. It deepens your understanding of how software is built and run and helps you write better, more efficient code. There are many resources available to help you get started, from online tutorials to textbooks and courses. Every programmer encounters compiling errors at some point. These can range from simple typos to complex logical mistakes. Understanding how to read and fix compiler error messages is an important part of becoming a skilled developer. Wrap up: compiling is a core concept in computer science that bridges the gap between human logic and machine execution. From transforming source code to optimizing performance and ensuring security, compiling plays a vital role in software development. Understanding this process empowers you to write better code and build more reliable applications. Thanks for joining us on this journey through the world of compiling.